How'd the homework go? Did it step up from chapter 1?
Yeah, it was 2 pages opposed to 1.
It is a pretty good assignment. Yeah. All right. Hey, well, I'll get us started here, and I'll begin by just kind of highlighting where we are and where we're headed as you guys come on. And first of all, as you know, last week we did our what I'd call our first week on physics, and that is our chapter 2. So looks like some of you turned it in on the way in. That's fine. The rest of you, or most of you probably, are going to turn it in on the way out. That's fine. Certainly don't bother to get up now and that we're getting started here and turn it in. Others of you, maybe you have 1 or 2 more you kind of want to finish up, or a question or 2, and you're going to turn into lab today, and that's fine too. Hopefully it went well for you. I would say that I think you saw a step up from chapter 1, where chapter 1 we were doing a lot of review type of problems. We weren't even really doing physics yet, some unit conversion, and then we got into those problems of motion here. And hopefully you also saw that they kind of matched what I was doing on Wednesday, and I just went through a bunch of examples. Meanwhile, let's go on to chapter 3. And like I said, you may have some more questions on that chapter 2, and that's fine. We just won't have time in class to deal with them directly. I hope you're taking advantage of Don on Fridays and going to the MC, and as you get to know him, you'll see him throughout the week. That's a great opportunity. I'll add to that, although I do want to emphasize that this is kind of a secondary help place, and that's our free tutoring service here. And so I guess I don't need quite this many. This is probably more than enough, but this will get us started. If you could take one of these and put it in your notebook and hang on to it, and I'll pick up the extra ones at the end of class. But this is our free, I should say, and keep saying that here, tutoring hours. We don't have a whole lot of them. It says it's in PS 112. It's just right down the hallway there. But there's about 3 hours each day. Looks like a little bit more on Wednesday and a little bit less on Thursday. And of course, for you guys, the big thing is the Friday afternoon workshop, which is why your homework is always due then on the Monday. And hopefully, by the time we go through the material on Monday and Wednesday, you get a chance to do a significant amount of work before Friday, and then ask any questions and do some more work on Friday. I guess in an ideal situation, you get it all done on Friday. You wouldn't have to worry about it over the weekend. And maybe that has worked for you so far. Our assignments get a little harder as we go along here, so I suspect you'll also be having to, struggle through them on the weekend. Anyways, that's just a long way of saying then that we've done chapter 1 and chapter 2. Chapter 2 was our first physics one. Let's take what we've learned and expand on it, and that's our next big step. And when I mean expand on it, here's what we're going to do. It's two-dimensional motion. What we have done, and I think you caught this, I said it a number of times, you probably saw that in the example, every problem we did was one-dimensional. Now, I say one-dimensional, but I don't mean horizontally only. You did some problems that were vertical. You did some problems that were on an incline. What you did not do is a problem such as a car going, say, 45 miles an hour, exits the freeway, continues to go 45 miles an hour, and then merges onto a highway going 45 miles an hour. That is two-dimensional, right? We were going this way, let's say north. And so the car is going 45 miles an hour north as it is exiting, goes on this off-ramp, if you will, but continues with 45, merges onto the highway, now it's going 45 east. Did the car accelerate?
Yes.
Yes or no? Okay, so some of you are shaking your head, But what this does is open the door to two-dimensional motion. And so we've only dealt with one-dimensional motion. In fact, maybe it's worthwhile to put some numbers here on the board. Let's say a car was going this way, and let me get away from miles per hour. Let's say a car was headed in this direction at 15 meters per second. And this room is kind of laid out north this way, so let's call this west. So the car is going west at 15 meters per second, and a second later it has sped up to 17 meters per second. Now it's still going west. So this is the type of problem you just got done doing. And I would ask, is this car accelerating? Well, most of you are shaking your head yes. Okay. What is the value of the acceleration? What was the definition of acceleration? Was what? Yeah, it was change in what? What goes here? Yeah, is it velocity or is it speed? And is there a difference between velocity and speed? Yes, there is. And we didn't make a big deal out of it quite yet, but now as we get started in this next little part, let's really emphasize this. This is a big difference. We've only done one-dimensional motion. You guys probably recall from Physics 102, what's the difference between speed and velocity? Velocity is a vector, is the fancy word. It has direction. And so the definition of acceleration does have a change in velocity. That's the key thing I want to begin today and emphasize. And so a change in velocity can come in two different options. One, it can change its speed, but two, it could change its direction. And now you begin to see where I'm heading here. What we just did in the last chapter, something like this, I would have said the acceleration is, and I would have gone 17 meters per second minus 15 meters per second. Let's say it took 1 second to do that. I would have said the acceleration is 2 meters per second each second, which simplifies to 2 meters per second squared. That's the kind of problem we just got done doing, a one-dimensional type of problem. The fact that the car, if it is going to accelerate, means it either goes faster or slower. It could not change direction because we limited our discussion to only one-dimensional motion. We didn't allow the car to turn. And so now I ask this question as we get ready for our next big step. Here's this car going one direction. I'll call it north. It's going 45 miles an hour. It banks along a turn and it goes 45 miles an hour the whole way. It is now going 45 miles an hour east. Did that car accelerate? Yeah, and most of you are shaking your head yes. Why would you say yes to that question?
No, velocity in the north direction.
Okay, it changed its direction, right? And so the whole idea here of an acceleration, if there's a change in velocity, and a change in velocity could be a change because its speed changes, but it can also be a change because its direction changed. And so our first big step right here is, again, if a car then turns, so now it's a two-dimensional type of problem. And in this case, I'm deliberately talking about a car that would be turning, so its direction is changing, but its speed is not. And of course, you are answering correctly. Yes, it's accelerating. So let me make the next step. What is the value of the acceleration? You didn't seem to have any troubles with the question here. It was going 15 and sped up to 17. What's the acceleration? I bet if I asked you this, that the car was going 15 meters per second and then it slowed down to 12 meters per second in a time frame of 1 second. I bet you could tell me the acceleration there too. What would it be? Yeah, you would go, well, it's going 12. It was going 15. It did all this in 1 second. That is a decrease of 3 meters per second in 1 second. That would simplify, and you would have told me that the acceleration, and most of you did, the acceleration is 3. So no problem in the one-dimensional, right? You told me the acceleration here, you gave me a 2 meters per second each second, and a positive. You gave me a negative here, a negative 3 meters per second. So let's take that next step. What if the car is going this way? And I guess I now put some numbers on the board. Can I get away from miles per hour? And let's go back to the metric system here. Why don't I take roughly about 20 meters per second? That would be kind of roughly 45 miles an hour. And in this case, it was going north. And a little bit later, it is now going 20 meters per second east. Did the car accelerate? Yes. What is the value of the acceleration?
Well, if it did it in a second, would it be negative 20?
And it sounds like some of you kind of got the idea, but a lot of you got some mathematics to learn. And good, because that's the layout of here. Because if you look at your syllabus here, you will see that today's topic is chapter 3, and it is on the mathematics of dealing with two-dimensional motion. It is a short chapter. It's not really a physics chapter. It is more of a math chapter to answer this question. How do I take 20 north and subtract it from 20 east? It was a lot easier in the last chapter when it was all going to the, I guess I said west here, and I didn't say which way, but maybe I implied west here. I could even probably have done a west and an east, but as long as it was one dimension, we just used pluses and minuses. What do we do when we have the 4 directions on the compass rose? Or better still, we have the 6 directions, because we may go up and down as well as north, south, east, and west. How do we handle a change in direction mathematically, as well as a change in the magnitude? And that's what this chapter 3 is. And so I would put chapter 3 and 4 together. And today, then, is a short one. It's chapter 3. And so Wednesday, we will really get started with more physics of two-dimensional motion. We got to spend some time dealing with some mathematics here. And so that's where I want to begin here with a summary of where we're headed. These two chapters go hand in hand. The first of these two, chapter 3, is short, pretty straightforward, and then it gets a little harder when we try to use it in the next chapter. So you see this question here? Let's hold off on it. Hopefully before today's over, we can answer this question numerically. What is the acceleration of this car that started off going 20 north and ended up going 20 east? Did it accelerate? Well, you already said yes. What is its numerical value? Well, let's wait an hour for that one. And so I'll come over here and say, let's do some mathematics. I don't know if I should call it a mathematic review, because for some of you it is a review, but for others of you this will be new. I bet this beginning part would be a review for everybody, but so let's see how it plays out together here. I'm going to start with just a coordinate system. And so I guess really I'm probably taking you back to about 7th grade mathematics, where you begin to learn a grid. A Cartesian coordinate system, a rectangular grid. If I come up here, you at some point along in your education, no doubt, labeled an x-axis and a y-axis. And so we're going to do the same. That's going to be our grid here. Looks like this one's getting kind of dry here. Let me switch for a second. And so I'm going to then do like I said, a math review here, starting with a grid. If I were to put a point right here, I'm sure you learned that we could label that point, right? X, Y. And of course, that's what we're going to do mathematically. This point's going to move. This point could represent the car that I've been discussing. It could mention, maybe a three-dimensional movement, like a bird, that will go north, south, east, and west, and up and down. And then we would have a z-axis. But I think it'll serve us well just to start with two dimensions, x and y, and then we'll add a z-axis as we go further here. But I think you remember what that means. It means that I can move, say, along the x-axis so many divisions. Let me just put 4 divisions here. And I probably didn't give myself enough space to do it well, but let's call it 3 divisions up. And so in this case, I would label this point as 3, 4, right? Whoops, got it backwards. Try that again. 4, 3. So I would have 4 steps in the x direction and 3 in the y direction. Fair enough? And that's a Cartesian coordinate system. That's not the only coordinate system you used. It's probably the first one you learned, and it's probably the one you've used the most. But there's another convenient way to write the location of that point. We called it in math a polar coordinate system, right? What do we mean by that? Well, on that one, we meant something like r theta. R representing how far is that point from the origin, and theta representing that angle. So in this case, I picked a simple one. Maybe I should even ask you, what would be the value of r be? Okay, good. I hear somebody doing Pythagorean theorem. That's good, although this one I think is a little easier than that. This is one of the special right triangles, right? It's the 3, 4, 5 right triangle. And so I was just kind of assuming you kind of remembered that one. The angle, you may not remember. We could probably go through some math, and I will in just a second. But the angle here is roughly 37 degrees. And that's where I want to go through some mathematics. If you know one coordinate system, don't you know the other? You're about to see that a typical problem when we get to chapter 4, so not today, but Wednesday, will begin something like this. We will take an object, let's just say it's a rock, and we will throw the rock at some speed and angle. Okay, right there, that's a description of what is happening, but it's a description in polar coordinates. Now, you guys might remember from Physics 102, when something moves across in a two-dimensional motion, how do you solve a problem like that? What do you do? What do you do with the, say, horizontal motion and the vertical motion? You separate them, right? In other words, two-dimensional motion is really just one-dimensional twice, right? And so one of the first things you learn, and this is what I'm getting at here, although just like our 102, although we will be more mathematical, the first thing we have to do is figure out if you're going to throw this thing at an angle, how much of that speed is horizontal? You have to get what we'll call the x component. We'll have to go through a little trigonometry to get the Cartesian coordinate. And there it is. Your first big step when solving two-dimensional problems will be, it will be described to you in terms of polar coordinates, and you've got to figure out what that is in Cartesian coordinates. Because as you guys may or may not remember, you treat the horizontal motion separately, and you go through all your calculations to where is the object going to be, and then you do the y, and you treat all the y motions separately. And then usually the very last step is you finally figure out how fast is this thing moving in the x direction and how fast is it moving in the y direction, and you put those two together to get the total speed. In other words, you convert back from Cartesian to polar. And you're about to see that. Now, granted, that's not today, that is Wednesday, but what I'm trying to set you up for is the reason we need to take some time to make sure we're good with our math is in any given problem, you will probably start with polar coordinates. Before you can solve or do any manipulation with it, you need to go to Cartesian coordinates. Before you can give the final answer and answer the question, what angle does the rock hit the ground, you've got to convert back from Cartesian coordinates into polar coordinates. And so that's why your author has put this chapter here. He's going to do some mathematical review. And this first one is just a simple coordinate system converting from one to another. So let's run through that here. Let's do this. Let's say that you were given r and theta. Like I said, that is kind of the normal process. You are given this distance r and this angle theta. Now in this one I actually gave some concrete numbers to them, so we'll continue to use those numbers, but in general then, how would I get x? How would I, starting with polar coordinates, go into Cartesian coordinates? Like I said, that's going to really be your first big step. Right, and there's our trig for us, right? And so again, let's talk a little bit about our trigonometry. Maybe I'll do it right here, but if I were to put something like cosine of theta, looking at this triangle here, this bottom part I would call x. The up part, I guess I'd call y. The hypotenuse is r. The angle is theta. What is cosine theta? Adjacent over the hypotenuse. And so the adjacent would be x. The hypotenuse would be r. If I moved the r together with the theta so that the two given ones are together, I can then get that x. And hopefully that looks like a nice review, because believe me, you're going to be asked to do that so much. You're just going to want to know this second nature without thinking about it. Here's what I would suggest, by the way, and it really falls down to this category is, I bet in your math class you learned your trig function that way. And of course it is correct. But this will serve us much better, because notice it has the two polar coordinates on the same side. That's usually what is given. So you're given these two and you're asked to find the x. Now that's not to say you can't start here. In fact, some of you will probably feel more comfortable starting here, but I will tell you, by the time we get into chapter 5, now that's a ways away, we've got 2 chapters to do, plus a test to take, but when we're in chapter 5, hopefully it'll become second nature for you to see that this is the same as that. Here's how I like to think of it is, look, I want to know the x component. That's a component, that is a piece of the triangle. It's not the whole triangle, the whole length of it is always the hypotenuse. So if I take the hypotenuse times a little bit, and so I'm going to say it this way, magnitude times the component, right? That will give me the component. Or I'll say magnitude, component, and soon I'll say direction, because right now it could have been positive, I could have to go in the other way, and negative. but there'll be magnitude component and then a direction to go in here. Okay. And again, maybe that's so obvious. I hope it is. I hope a lot of these things in this chapter is obvious. I know in past semesters, students just breeze through chapter 3. They go, those are pretty obvious. Good. But for some reason, when they actually try to put it into practice in chapter 4, it really bogged them down here. So make sure you understand why you do each little step. Okay? What does cosine mean? In fact, maybe this will help a little bit. Let me label this angle up here. How about I call that angle alpha there? What would cosine of alpha be? Good. You see that it's a y over r, right? The cosine always means the adjacent over the hypotenuse. It doesn't always mean x over the hypotenuse, doesn't it? Fair enough? And so be careful with that, because in this case, if I were to rearrange it, I would get the value of y is equal to r cosine of alpha. And so notice it's giving me y, yet I'm using a cosine. Well, it kind of makes sense. I'm not using the traditional angle as measured from the x-axis. If I use the traditional angle as measured from the x-axis, then cosine does go with x. But if I use some other angle, cosine doesn't necessarily go with x. So again, just to help you with your mathematics, hopefully you remember cosine function as it's the adjacent piece. It's not necessarily the x piece. Well, I should continue this discussion here. Why? How would I find y given r and theta? Yeah, and again, maybe you can see that if I were to write out here sine theta. All right, now look at this triangle. Sine theta. Now remember, sine means opposite. And again, I'd encourage you to remember as the opposite, not as y, but as opposite, because we don't always use the traditional angle. And as I look at opposite, it would be opposite over hypotenuse. And that would be a y over r. And again, just like we made that statement earlier about the cosine function, I bet many of you have learned your trig function sine this way as a ratio, but it's going to serve us better to move that r over to here. And so we have the r and the sine theta together. So that, again, we're answering that question. If I'm giving r and theta, could I get y? If r and theta, could I get x? Could I convert? And hopefully quite quickly, because like I said, in chapter 4, and particularly in chapter 5, we've got a lot of other things we've got to solve for. And so our brain power should not really be consumed here on converting from a polar to a Cartesian. That's what we're going to learn now in chapter 3, but it's hopefully going to be such a habit for us that we won't even have to think about it anymore. And again, I think this is the best way to do it. Instead of this way that you probably learned in your math class, think of it this way, is this is the magnitude and I want a component of it. I don't want the whole magnitude. Again, the rock was thrown at 5, but the question is, how much is it going up? And so I want the opposite of that angle. So it is 5 times the sine of, in this case, 37. That would give me my y. And maybe I should double check all of this, but if I get my calculator out and use the numbers I gave you over there, 5 being the hypotenuse and 37 degrees being the angle, and let me just see what mode I'm in. Yeah, I'm in radians. Let me switch over to degrees back. Okay, all right. So 5 times cosine of 37, and this lists at 3.9. No. I think 36.7 is a more accurate angle there, but I just kind of rounded it. And the same thing here. This is 5 times the sine of 37 degrees. And so 5 times sine of 37 is 3.01. So yes, it does match. And so, again, just kind of developing that skill. Can you go from one coordinate system to another, right? And so in this case, you're going to see that. That's going to be the very common first step. Rock is thrown with some speed at some angle. And in order for you to continue to do a calculation, you really are going to need to know how much speed is in the x direction and how much speed is in the y direction. And we get there with our little trig functions. That was the nice thing about our trig functions. We can take a triangle and figure out what the sides of the legs are. I should say right triangle. Okay? And that's the purpose of this chapter, is to get you to remember those math skills. Because again, we really need them as we start looking at our two-dimensional motion. And let me continue on here, because the other part of this then is once you start manipulating it, you know, this is, say, the beginning speed in the y direction. And then 3 seconds later, there's going to be a new speed. 3 seconds later in the x direction, there may or may not be a new speed if there's just gravity, which you probably remember from 102, only affects it in the y direction. So maybe this won't change, or maybe it will. But whether it does or not, after a couple of seconds later, you're going to have a speed in the x direction and a speed in the y direction. So let me just add to this. Given x and y, could you get r and theta? And so there's the reverse process. And so again, this is the first half of this chapter, is just kind of a little mathematical review on how do we convert from one system into another. And like I said, you'll see that right away in chapter 4, and more so in chapter 5. All right, well, I heard you guys say it already. Talk to me. How am I going to get r?
Pythagorean theorem.
Yeah, Pythagorean theorem, right? The sum of the squares of the leg equal the square of the hypotenuse. So if I then take the square root, that should give me the r value. And so, of course, be prepared to do that many times, because, as I said, here is a typical problem. The rock is thrown at some speed at some angle. What angle and at what speed is it headed 3 seconds later? And of course, in order to do that, step number 1 is right here. Convert it into its x and y component, and then find out how those speed changes after 3 seconds. Once you can do that, now you have that speed 3 seconds later. To get the total speed, you got to put together what I'm going to call the x component of the speed and the y component of the speed, and we do that with Pythagorean's theorem. And so that's how you're going to get your r. And of course, how do you get your angle here?
Inverse sine of y over r.
Yeah. We can do an inverse sine, or arc sine, of, and in this case, I guess I would have opposite, which is y, over the hypotenuse. Couldn't I also do an arc cosine? Okay, which I guess would be x over r. And that's what I heard 2 of you guys say, and that is correct. I wouldn't want to disagree with that. Although this happens to be using the r, not just the x and y. So what I was thinking, and of course all of them should be true, was the arc tangent. The arc tangent would be opposite over adjacent, right? And so it doesn't matter which of the 3 trig functions you want to use at this point, assuming you've already made that step. Now, if you didn't make this step and they just wanted to know angle, then probably that means we're going to go to tangent. And I do that probably most of the time by default. And even though sometimes I have r, it kind of just depends how the numbers work out. But all of those would be true, and that would be your angle. And based on the look at your guys' face, you're like, yeah, okay, I got that, we've done that. And that's good, because that should save us some time, and we should start getting into examples, and then you'll see it in practice. And if you're going to have any troubles, that's probably where it will be, when you actually are kind of forced to not only do the calculations yourself, but I think one of the harder steps is to realize you're supposed to do the calculation itself. That's a big one here. It's like, oh, I was supposed to do an inverse tangent. Okay, and then once you realize that, then you can actually do the inverse tangent. But before I leave this too much here, I just want to keep emphasizing here, and I'll put a dotted line around this one. We don't always use the cosine to get the x, or the sine to get the y. And of course you saw that already right here. Here is using the cosine, but it gave me the y. Could I get x from the angle alpha and r? How would I get x? Yeah, and again, good. Noticing it's a sine here. The sine of alpha. And I'll say it again. Don't think of sine as the y piece. Sine is the opposite over the hypotenuse. And so there's the alpha. The opposite is x. And of course the hypotenuse is still r. And so moving that r over to here, I can write this as r sine alpha equals an x. And so of course using the traditional angle x, theta measured from the x-axis, the x and the cosine go together. But we don't always do that. And so sometimes we come across non-traditional angles like alpha. And so that's what I'm pointing out. Got to be careful with the basic meaning of our math. And as I said before, read that math and understand the math. Don't just do the math.
We're going to approach cylindrical probably a little later. Yeah.
Well, I haven't done it in any three-dimensional here. But yes, we could add a z direction onto this. And you do have one or two here in chapter 3 homework, so I should add more to it as we go along. But as you can see, the first discussion is just two-dimension, and then we'll go one more. Anyways, I think you see that. In fact, as long as I'm here, how would I get the angle alpha? Yeah, and I can do the same thing. I can do an inverse tan. I can do an inverse sine for that matter. Or I can do an inverse cosine, right? But I was thinking about the tangent just because it has to do with the Cartesian coordinates. And so what would the tangent of alpha be? Yeah, x over y. So in this case, I want an x over a y. So again, notice, when you're looking for an angle and you're taking the inverse tangent, it is not always y over x. It can be x over y. And so think of it as opposite over adjacent, not as y over x. And then you'll be fine. Again, sine of the angle. Well, again, sine means opposite. So the opposite of alpha is x. And so this would be an x over the hypotenuse. And the opposite of, sorry, not alpha, the opposite, but cosine is adjacent. So if I look at this angle, the adjacent is right there. Well, that's the first half of chapter 3. As I told you, it's not a real long chapter and not a real hard chapter, but perhaps a couple of new things will show up. Maybe none of what I did already was new to you. Maybe this alpha representing with the x and y switching roles might be new to some of you. If not, great. But if it is, just keep that in mind, that always think of your trig functions not in terms of x and y, but in terms of adjacent piece, opposite piece, and hypotenuse. And then you can look at your geometry. All right, well, I'm going to keep going here because there is some nice mathematics that will kind of help us describe this. Again, let's come back to this little triangle here. So here is this ball, as we said, was thrown. And the numbers I put in here were 37 degrees at an angle 5. And as you can see by our math earlier, we really said that this ball then has really two components. What you're really saying is it's traveling at 4 horizontally, right? It has an upward speed of 3. And so sometimes it's nice to represent that. In other words, we could say something like, okay, let's look at, oops, I shouldn't say speed. I guess I should say velocity. Now it has direction here. But I can look at this and say, here's the velocity. And of course, one way of saying that, as we said, is it is 5 meters per second at a 37-degree angle. Oh, and let me just put above the horizontal. See, again, that's this polar coordinate system. But I think as you're seeing here, another way of saying that same idea is to say it really has a speed of 4 meters per second in a horizontal direction and a 3 meters per second in a vertical, right? That's what this math had described. Now, here's kind of nice. What if I had written this? 4 horizontal, 3 vertical. I bet you would have been bothered a little bit, right? I mean, what's missing here? Yeah, I mean, are the units, are they important? Yeah. I mean, is there a difference between, say, 4 meters per second and 4 centimeters per second? Well, absolutely, of course, right? And so that little piece of information is valuable. And in fact, in chapter 1, isn't that how we started this class the week before last? Didn't we say the units were important? In fact, the units, why did we write them with nothing in between? Is because the units were really a multiplication, right? Back in chapter 1, I started that whole chapter on the Wednesday of the first day and said, why do we write the distance from this door as 10m? Because what we really meant was an m, and another m, and another m, right? The 10m. We really meant multiplication. So right here, we're missing something very important, and there's multiplication here. But what about these? Are these important?
Yeah.
I mean, so this would really bother you, but I bet this would bother you too. Oh, it's going 4, it's going 3. Yeah, it's going horizontal and vertical, sure, okay. But that's not a real good description, right? I mean, what's missing here?
Direction.
Yeah, you're not really saying what goes with what direction. I mean, is 4 meters per second horizontally and 3 vertically the same as 4 vertically and 3 horizontal? So isn't the direction an important piece here? And isn't it really just as important as the units and the numbers? And so just like you would never want to have a number without the units, you wouldn't want to have a speed that had numbers and units but not specifying its direction. So for some of you, you've seen this. We need a new number. A number perhaps you have not seen before. A number that says x direction. Watch this. Let's get away from speed for a moment. If I were to stand here at the door and take 4 steps, 1, 2, 3, 4, that's the x direction. Isn't that very different? And I can't physically do this. 1, 2, 3, 4. If I took 4 steps in the y direction, right? And so we're going to invent a new number. A number that says you did this, 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 and this. And so here's our new number. It is the letter I with a little hat over it. Now, this letter I is not the square root of -1 that some of you may have been exposed to. This little I with a hat over it means 1 in x direction. So if I wanted to mathematically describe 4 steps in the x direction, where each step is a meter, how would I do that?
4I with little hat.
Yeah. 4 meters I hat direction. Because what this means, right, is an I plus an I plus an I plus an I, where each, there's the 4 I's, and each I is measured 1 meter long. Does that make sense? And of course, the easy way to write 4 steps is 4 I hat. And let me now forget, my unit is measured in meters. And so, we have, I will call a new number. It's actually what we're going to call the component piece of it. But treat it just like you would any other mathematical property. Just like we were saying in chapter 1, treat your numbers and your units like any other mathematical property, because that's what they mean. And so in chapter 1, when I said the distance from that door to that door was 10 meters, what I really meant was m plus m plus m 10 times. We can expand what we learned. We should really be saying the distance from that door to that door is really 1 step in the x direction, another step in the x direction, another step in the x direction. All of these were in the x direction. There were 10 of them. And each one was measured in meters, and so it's 10 m I hat. That making sense? And I suspect this new number, if you will, is new to some of you. But hopefully you're also seeing I am now creating the mathematics of how do I deal with direction. I already know how to deal with numbers, and I already know how to deal with the units. And the new piece of the puzzle is how do I distinguish between something moving in the x direction and something moving in the y direction. And this mathematics will do it for me. Yeah.
So the I with the hat over is going to come after the other units?
Well, and of course, now this is multiplication, so it doesn't matter which way I multiply them out. Right? I mean, isn't 5 times 4 times 2 the same as 2 times 5 times 4? So I would say which order I put it in really is irrelevant, but the tradition is to put the number first, then the units, then the direction.
Okay.
And so, yeah, I would encourage you to do that same thing. Yeah.
So is there like a number for y direction?
Ah, yes, there is. It's going to be a j hat for the y direction. Okay. And so let me build up to that here. But the whole idea then is that you, in the second half, and some have been exposed to unit vectors. Some of you have been not. In fact, in the past, when I've asked for a show of hands, about half the class has risen their hand. Maybe I should ask again. How many have seen this little I hat unit vector? Okay, well, this time it's clearly more than a half here, so all right. So you guys are just such a smart group. We can go, all right, a lot faster and give you a lot harder problems on the test, right? No. But that's that little I hat. So again, that's the two big steps for this chapter, is coordinate systems, rectangular and polar, and converting back and forth. And the other one is describing then not only the numbers and the units, but also the direction. And you're going to see this is going to be a real powerful tool here as we work things out here. And so, well, you guys brought it up, and since a lot of you have already seen it, I'll leave the I hat alone for now and go to the J hat. And so if I added a little J with a little hat on it, you guys probably know, what do you think it means? Yeah, it's one little step or one little unit in the Y direction. And maybe for completeness, I'll put a K hat. Any guesses what K hat might be? Yeah, this is one little unit or one little step in the Z direction. And again, I haven't done much with the third dimension, and nor should I don't think quite yet. But now this really helps me back here. Remember this whole description about tossing the ball. To make it real clear and mathematically useful, when I toss this ball, instead of saying I tossed it with a speed of 5 meters per second and an angle of 37 degrees above the horizontal, what I can do is I can get out my calculator and find out how much of that speed is in the x direction. By taking the 5, multiplying it by cosine of 37, that's where the 4 came from. And I can also find out how much is in the y direction by, again, taking the 5 multiplied by the sine of 37 and get the 3. And then I can write the speed as a 4 meters per second in the x direction. And in addition to that, or I should say at the same moment, we also have a speed of 3 in the y direction. And we like to do one more thing here. To distinguish that directions are important, we're going to call these vectors. I heard some of you already say that. A vector is what?
Speed and direction.
It's a quantity that has both a speed and a direction. Some measurement, some quantity in the physical world, direction is absolutely important. For example, does speed need a direction? Is there a difference between going, say, 5 meters per second north versus 5 meters per second west? Huge difference, right? And so direction, I would say, is really as important as the number itself. I mean, if I would ask you, is there a difference between going 5 meters per second north and 100 meters per second north? You would have said, well, yeah, one's a lot faster, right? There's a difference between those. And the way we describe the difference in the magnitude of them is very clear. We have a different number. And likewise, if I would have said, is there a difference between 5 meters per second and 5 centimeters per second? You would have said, oh, absolutely, right? The units are just as important as the numbers. You can't correctly describe what is happening until you include both the numbers and the units that go with it. You can't just stand here and say, which is bigger, 2 or 10? Well, if there were only numbers, you would probably pick 10. But if these are distances and I said, which is bigger, 2 feet or 10 inches, well, it's pretty clear. 2 feet is quite a bit bigger than 10 inches, right? And so those units are absolutely important. And that, I know you already know, that was chapter 1. But this one is also saying exactly the same thing. Is the direction important? Yes. And a lot of physical quantities include a direction. And when they do that in the physical world, we call those a vector. So velocity is a vector. distance is a vector, or I should say displacement. Because if I go 5 steps this way, that's very different than going 5 steps that way, or that way, or that way. And direction does matter. Now that's not to say everything is a vector. If you were to ask how many gallons of gasoline are in the tank of your car, that's not a vector. It's a number. I've got, 7 gallons. Makes no sense to say I have 7 gallons north. Right? And so not all measured quantities, not all quantities in the physical world need to be described with a direction, but many do. And so our description is not complete until we include all 3 of them. And so you can see why we spend some time here to say, look, you need a number, you need the units to measure that number, but you also need something to describe its direction and something we can work with mathematically here. And so there is my velocity vector. And that's when we put this little arrowhead over here. It's a vector. This is something, this is a quantity where the direction is important. It's not how many gallons of gasoline do I have, or what's the temperature outside. I mean, it's great to say temperature, oh, nice day, it's 70 degrees outside. Yeah. You wouldn't say it's 70 degrees north. It makes no sense, the directional part of it. Okay. And so some quantities need a direction, others do not. So this is that idea. Now, let's draw this in picture form. I've been talking a lot so far about velocity, mostly because that's what we're going to hit first when we get into the next chapter. But sometimes I think it's easier to visualize this in terms of distance. So why don't I say position vector, r. And let me just do the same numbers. 4 meters, I hat. 3 meters, j hat. And I'll call that a movement or a position of number 1. Let's kind of change what I've been talking about. I've been doing kind of like a plane grid vertically up and down. But if I move this down so I can actually walk, that what I'll call R1 kind of looks like I would take 4 steps. 1, 2, 3, 4. And then in the y-axis, 3. 1, 2, 3. And so hopefully you can see in the mathematics that that's what it's saying, right? Add them together, right? They're 2 pieces. And so in a little picture, I would say this is 4, and then 3. There is vector R1. 4 over, 3 up, right? Or in this case, 3 towards the board. And of course, now written in this way, I would say this is written in its Cartesian form. Of course, could you write it in its polar form? And so what you are really saying here is that this 2 combinations, right? And that's why we write it as a plus sign. This is a movement in the x and then a movement in the y. It's 4 steps in the x and 3 steps in the y. That's equivalent to, and I probably don't have to do the numbers anymore, 5 steps at an angle of 37, right? And so again, I can write this as a polar coordinate, or I can write this in a Cartesian coordinate. And this is a Cartesian coordinate that's very mathematical. Because didn't we start this whole discussion with me asking you how you're going to how you're going to get the change in velocity of that car that's going 20 meters per second? Haven't forgotten that problem, have you? And then a second later, it is now going 20 meters per second to the east. How are you going to subtract those? You need a mathematical process to handle direction. Not just the numbers, Not just the units, but direction. And that's what this discussion is all about. We are learning that there is a nice and convenient mathematical process for handling direction. These little I-hats and J-hats will do it for us. Yeah?
When you converted the 4 meters I and 3 meters J into the polar coordinates, so
right.
you write 5 meters Ji times I.
Oh, no, I mean, okay, so I guess I would then write it this way, that the magnitude, and then we usually put a little box there, of that is 5 meters. Its direction then, theta, is 37 degrees. So we don't have any, I-hats or J-hats. We've got completely away from the Cartesian coordinate system. Sometimes we also just do R1 without a vector over it, which is then saying what's the magnitude of it. So don't be surprised if you see it written this way or this way. This is kind of the short way. This is nice to write it. This one emphasizes that it's a vector, but I'm after how big is the vector, not its individual components. Okay. Oh, let's do this for a moment. You see that R1? Keep that in mind, that I have R1. But let's say I have another vector. Another little walk, if you will. This first walk can be thought of as either 5 steps at an angle of 37 or the equivalent of 2 of them. But let's just think of it for a moment as 5 steps at an angle of 37 degrees. And then I get right here, and again, still calling that the x-axis. Let's say that I turn, let's just go 40 degrees, and I take 8 steps. I'm going to run out of room, so I won't take the full 8 steps. But maybe I finish right over here. Where am I from my beginning spot? I mean, I guess if I'm drawing a picture, I guess it looks something like this. The first one says, take 5 steps at an angle of 37 degrees. This is that R1 vector. But now, I'm trying to say there's a second little motion, R2, which its magnitude is 8 steps. And let's say each step is a meter. That's probably a little big for a step there, but 8 meters. And you might want to say it's at 40, what did I say, 40 degrees? And I don't know if you want to call it down, because I don't want to imply that I'm going under the ground. But when I draw it on a board, it's down. It's, the negative rotation. So I'll go ahead and call it down. So up here, I'll just draw a little dotted line and then put 40 degrees. And then that distance is 8 meters. Where am I? Do you see where you're adding these two together, right? Aren't you adding an R1 and an R2? Your author uses the word resultant, R. What is the resultant of these two vectors? What do you get when you take R1 and you add it to R2, right? 2 little vectors. The first one has a magnitude of 5. The next one has a magnitude of 8. Am I going to be 13 away? Does 5 and 8 make 13?
Yes.
Not anymore. Right? I hope you noticed that back here. 4 and 3 makes what? 5. Right? Because we include in this part the direction. And so if you took 4 steps in the x direction and 3 more in the y direction, that's the equivalent of taking 5 steps here. And 4 and 3 only make 7 when they are in the same direction. And likewise up here, this little motion here of 5, this little motion of 8 will not be (13). That is not a resulting vector. But you can find it. At least I hope you can. Now we're kind of getting to the final steps of this chapter. I think you begin to see then what we refer to as the components. You see, we've already done R1 and said this is 4 meters in the I hat direction and 3 meters in the j hat direction. And what I'm going to do is add to that vector number 2. And before I can plug in vector number 2, let's talk about vector number 2. You see, vector number 2, I described it to you in polar coordinates, didn't I? I gave you the distance was 8 and I gave you the angle. How would you get it in Cartesian coordinates? And in fact, I should even ask, why would I want it in Cartesian coordinates? And hopefully you're seeing here that this first one has given you an x and a y. The second one, x and a y. Isn't this together what I would call the total x motion? You see, for me to figure out where I am, I need to put the x's with the x's, don't I? I don't want to mix up any of the vertical motion. That's irrelevant when I figure out how far did I move in the x direction. And likewise here, this I would call the total y motion. And my first little part I went up in y, and my second little part I went down in y. And in that case, I want to put y's with y's. But I never want to add something that's an x motion with a y motion. Can you see that in the graph? And now then, can you see the whole benefit of this mathematics? Because with this mathematics, this component and this component are not like terms. You cannot and should not combine them together. You should not combine them physically. You will not combine them mathematically because they're not like terms. And so now you begin to see the power of this mathematics. I can come over here and say vector number 2 can be really thought of as how much of vector 2 is in the x direction and how much of vector 2 is in the y direction. And this gives me a chance to give you a little bit of new notation here. That's what I'm really saying, right? How much of number 2 is in the x, and how much of number 2 is in the y. And of course, this takes us back to the beginning of the lecture. How would I get how much of this second little vector, R2, how much is in the x direction? Well, it would be that piece in my picture, wouldn't it? And if this is 8, I would want the adjacent of that 40 degrees. So I would want 8 cosine of 40 degrees, and maybe I should put 8 meters. That would give me the I hat direction, right? That's our conversion from polar coordinate into Cartesian. And of course, how would I get the y component? And looking at this picture, this would be the y component. So there's the 8, and then I'd multiply by sine of 40, right? Sine. But it's downward. And so this is the first time I did one with a negative. I would write it as magnitude components And the direction is a negative j hat. Maybe the first time I do it, I should put the negative with the little notation we mean by steps. And so instead of taking steps in the positive direction, I am taking steps in the negative direction, which more means I can put it out here. So this is 8 meters cosine of 40 I hat minus 8 meters sine of 40 j hat. And that would be vector number 2. I'd need to get my calculator out to get some numbers here. But it would be 8 times cosine of 40. That's about a 6.13 meters in the I hat direction. 8 times sine of 40 is a 5.14 in the j hat direction. That's what this notation would be telling me. This last little piece, although I took 8 steps off in that direction, it would be the same as had I gone this direction, 5.14, and then 6.13 in the x direction. And I'd end up somewhere over here. So now I can come over here and put this in. This is 6.13 meters in the I hat direction and 5.14 meters in the j hat. Negative. I should put that there. And that would be the total motion. And so again, maybe now you're beginning to see the power of the mathematics here, because really what I did was just 2 little walks, but I got 4 terms up there, right? The first little one was 5 steps off to here. Then I turn and go 40 degrees this way and take 8 little steps there. And what I'm trying to say is my first little walk, which was 5 steps at 35 degrees, is the same as doing these 2. Not that I actually did those 2, but it's equivalent of those 2. And then likewise, I took 8 steps at 40 degrees. I didn't really do a 6 and a negative 5, but they're the same as that. And now I can combine them together. And I'm hoping you're seeing in this picture then, what I would be doing is I would need to combine x's with x's. And that was the whole reason I wanted to make sure I took the polar coordinates that describe the problem and I converted them into Cartesian coordinates, because if you want to find out where you are, you would never put your vertical motion with your horizontal motion. You would only put horizontal with horizontal. So the I hats go with the I hats. And you can see that in the mathematics. When you look at this, this cannot be combined with that one or that one. They're not like terms. Now these 2 can. They're each like terms. And these 2 can. They're each like terms. And so when you're all said and done, this mathematics will force you to put x's with x's and y's with y's. So in this case, the 4 goes with the 6, makes a total of 10. And I guess we have a significant figure question here. But maybe I should have put 4.00. Actually, we had that number earlier. Wasn't it like 3.99? But pushing, so, well, I'll leave that alone, 3.99. I'll just leave it as 10.13. Even then, yeah, I'll just say that was 4.00. And then this one, of course, would mean that we would have a +3 and a -5. That leaves me with a -2.14 meters in the j hat direction. And so when this is all said and done, I'll grab the red pen here. Here's what it is saying. It is saying, where is this location? Well, it is 10 meters out, 10.3 meters, and 2.14 meters down. And I haven't quite finished the problem. If the problem is, how far are you from your starting point? What do? We're back to polar coordinates, right? We've got the x and y motion of it, but what is the magnitude of this resultant vector? And so the magnitude of this resulting vector then would be the motion in the x, the 10.13 meters horizontally, and then the 2.14 meters down, and I will add those together. And I say add them, I guess I really mean, fancy word is add them in quadrature, or Pythagorean's theorem, and see what the total length is here. So 10.13 squared added to 2.14 squared, and the square root of all of that is 10.35 meters. And so all that fancy math allowed me to tell me how far am I away. And so this was that starting point. Now remember, I really took 5 steps this way, here. Now I didn't actually do 4 and 3, but that's what the math is saying that's equivalent to. Good. And then I did 8 off in this direction, which again the math said I would be the same as going down 5 and over 6. And I would be somewhere over there, which would be the equivalent of 10. So those two together would have been the same if I had started here, turned at just a slight angle, and took 10 steps that way. And so that 5 and 8 is equal to 10. And to finish this problem off, what angle would I take? What small little angle would I turn to take these 10 steps? Well, hopefully you're seeing it here in the mathematics. I'll call that the angle theta. I'll label it up here in my little picture as theta. I guess we can debate if we should call that a negative or positive theta. I know traditionally when we go clockwise, right, that's a negative. Let me avoid that discussion for just a moment. Let me just find the magnitude of this. So the inverse tangent, the opposite, is 2.14. Again, notice I used the positive sign here. I'm not, again, really getting into the positive or the negative. Just what is the numerical value of that angle. So I'll just use the absolute value here. Then the x component, the adjacent component, I should say, is the 10.13. So if I go inverse tangent of 2.14 divided by 10.13, I get 11.9 degrees. And so again, this resultant vector of these two has a magnitude of 10.37 at an angle of 11.9 degrees below the x-axis. And again, if you want to stick to the traditional math way of describing it, you might say it's a negative 11.9 degrees. That's our traditional way of calling a negative rotation is clockwise. But that, then, is what this chapter is trying to teach you. How to add together two vectors. How do you deal with things that are directional important? And that's this I hat and j hat. And so if you caught what I did is I have just taught you how to add vectors together. And that's exactly what this chapter is trying to do. Although I guess I would say it's trying to teach you how to add and subtract vectors together. All right, well, let's give that a try. What about subtraction? Well, isn't subtraction just really adding negatives? And so I would go as far as to say is I have showed you not only how to add them, but also how to subtract them. Let me try this again. Let's put these two vectors here on the board. All right, so our first vector, R1, we've been saying for quite a time that it is 5 meters at an angle of roughly 37 degrees above the x-axis. And now the second vector, R2, which we said is 8 meters at an angle of 40 degrees below the x-axis, right? That's our two vectors. And a moment ago, we just combined those together. We added them. We said, what would happen if you did the first little one? Okay, so here's 5 steps. 1, 2, 3, 4, 5 at 37 degrees. Then 8 more steps at an angle of 40 degrees. And we figured this out, that would be the equivalent of about 10 steps off here, a little more than 10, at an angle of just shy of 12. Negative 12, if you will, right? Was adding them together. So what if I said, what is R1 minus R2? And maybe we should talk about what is R2. Well, as we've done earlier, R2, oh, did I erase it all? Bummer. R2 literally was 8 meters cosine of 40 degrees I hat, and then a minus 8 meters sine of 40 degrees j hat. Should I recalculate anybody? Was it I think I remember this. Was this a 6.13 meters I hat? And was this a 514 j hat? All right, good. So I won't have to get my calculator back out there. But that is really what we said our number 2 is. So what do you think negative R2 would be? Right, and here's why I'm saying that is, look, if I take, and I say, let's take R1 and minus R2, if we know how to add things, we also know how to subtract. We are just adding the opposite. And so, maybe not a surprise that the opposite, as the name implies, the negative, means you've got to go the opposite direction. But notice, it's not just the opposite of the x direction, it is also opposite of the y direction. That's the mathematical distributive property. So again, notice, how do you treat these new numbers called an I hat and a j hat? Especially for those of you who haven't seen them before. The answer is really simple. Same mathematics that you do for your numbers, you also do for your units, you also do for your I hats and your j hats. It's just another multiplication factor. And so, just like I would have done the distributive property, I would have taken anything out in front and multiply it by both terms. I've got to do that with this negative. I've got to take the negative and multiply it in front of the positive 6.13. That's going to give me a negative 6.13. And likewise, that negative has to be multiplied by this term, which has a negative already, so it's going to become a positive. And so negative of the vector, instead of going positive x, now goes negative x. And instead of going negative y, now goes positive y. Not a surprise. Let's draw a picture here. A picture would look something like this. The R1 would be this. So there's R1. The R2 was something that looked like that. So negative R2 is that. right? Negative R2 is the opposite of R2, right? It is, instead of going over positive x, it goes negative x. Instead of going down y, it goes up y. Not a surprise. And so again, this chapter is to introduce you to this I hat, j hats. I should say the first half is that conversion from polar coordinates into Cartesian, or the other way around, Cartesian back to polar. And the second half of this is to introduce you to these I hats and j hats, so we can add and subtract vectors. That's the whole point. Teaching you how to add and subtract vectors. I'll even mention, noticing it's not showing you how to multiply vectors. That day's coming. But we won't need it till chapter 7, so there's no point in discussing it now. We will discuss it when we get to chapter 7. But we're going to have to know how to multiply them. And we will learn that there are more than one way to multiply vectors. This semester we will learn 2 of 3 very useful ways of multiplying vectors. And so the first way is in chapter 7, and the next one I guess is chapter 11. So throughout the semester we'll add to our mathematics here. All right, so this right there is really, and let me use a new symbol here. Let's see, I used resultant R, maybe just a lack of better option. I'll just call it A vector. But then what I'm saying here is that A vector is the first movement minus the second movement, which what I'm trying to say is nothing more than adding the negative of vector 2. And so we've already been adding, so let's add now the negative. All right, so vector 1 hasn't changed. It's still this polar coordinates, 5 meters at an angle of 35 degrees, which we said, 37 degrees, which we said is the equivalent of 4 meters in the x direction and 3 meters in the y direction. And so there is vector 1. We are adding to that then the negative of number 2. That's how we get the subtraction. And so it's this number here, the negative 6.13 meters I hat and a positive 5.14 meters j hat. And so there's our 2 vectors. Okay? And so just like we did a few moments ago, after we do the conversion to Cartesian coordinates, so how much of this is in the x and y, how much of this is x and y, and the reason for that is we really can't do any mathematics until we have them in Cartesian coordinates. So we were usually given in polar, but the whole point of going to Cartesian is because we can't do anything until we're there. But then we can put x's with x's and y's with y's. And so like I said, our math would require that because we can only put like terms together. So this is going to give me a negative 2.13 meters in the I hat direction. And this is going to give me a plus 8.14 meters in the y direction. And isn't that what this vector kind of looks like here? There's vector A. The first one we did, vector R, was this one. Right? Where it went total of a positive x was 10.35, I believe, and then down, and we ended up in what you might call quadrant number 4. But this one's different. This one is ending up in quadrant 2. We've got the total result here is negative x and a positive y. That's definitely quadrant 2. And so that's what that little thing looks like. And again, usually we don't stop our problems here because usually what we want to know is how far is this then? Total distance. And so the last step of any problem is usually to take this Cartesian coordinates and go back to polar. And don't miss this. Some students miss this. They go, why would I start with it in polar? and convert it into Cartesian if I have to give my answer in polar. Don't I just stay in polar the whole time? No, absolutely not. Because to do any mathematics on it, what do you have to do? You have to be in Cartesian. But to give an answer that explains the physical world, we usually have to be in polar. That's why converting is, you know, kind of the challenge and part of the problem. How far is the end result? And you can't get that until you've added them up with Cartesian. So you got to go from polar into Cartesian. Once you get to Cartesian, you got to finish it by going back to polar. So how far is it? Well, I guess it would be a 2.13, technically negative, and you would square that. And then take the 8.14 and square that. Then I would take the square root of all of that, and that would give my answer of how far away is the result of these two. So 2.13 squared added to 8.14 squared, taking the square root of all of that, and this is equivalent to 8.4 meters. That's the magnitude of it. And so even though I took 5 steps that way and then 8 steps in the negative of those 8 steps, this would have been the same if I had just taken 8.4 steps off at some angle. And what angle would that be? And of course it depends where you measure the angle from. So I'm going to put it in my little diagram right here as theta. So I'm going to measure the angle from the vertical axis. That's not the traditional mathematical one, is measuring everything from the x-axis. Clearly, if I did it from the x-axis, it would be greater than 90 degrees. And so I'm not even going to mess with that. I'm just going to say it's from the y-axis here. And if I do an inverse tangent, then it would be opposite over adjacent. And so the opposite is really the x component at this point. That's the 2.13. And again, notice I'll just go ahead and put the positive. I'm just going to avoid the negative altogether. Obviously, I could do it both ways, so it's your choice on how you want to do it. But if I'm just after a number, I think this is the way to go, the absolute value. I was going to say, look, the length of that is a 2.13. The height of it is 8.14. And so my angle, inverse tangent, 2.13 divided by 8.14 is 14.7 degrees. And maybe just to make it clear, I should say from the positive y-axis. And say, okay, I'm gonna measure it from the y-axis. And I'll do positive also, I guess, to indicate the traditional rotate then to the counterclockwise direction. Yeah.
What would the tangent be in terms of r? Like, usually tangent is y over x if we look at it that way.
The tangent, okay, and I guess that was my point earlier. The tangent is not always y over x, right? It's always opposite over adjacent. So if I was looking, say, for this angle, let me call it alpha. Then alpha would be the inverse tangent of, and I need to make a triangle here. If I look at the angle alpha, the opposite is the y, which is 8.14. And the adjacent is the x, 2.13.
I missed that line upside down.
Oh, okay. And I'm kind of curious, then of course these two should add up to be 90 degrees. Let's just confirm that they do now that you see what you're saying here, that difference, 2.13. And so this comes out to be 75.3 degrees. And sure enough, these add up to 90 degrees as they as they should. And then, of course, maybe I should also say from the negative x axis. And in this case, I might even want to say up from the negative x-axis. But it'll serve me fine if this is during an exam. You can just put it in the picture and label it and say, okay, this is the theta I'm going to give you the answer from, whether it be from the vertical or the horizontal, positive or negative, doesn't really matter. Just kind of label it there and I'll know which one you're talking about. Yeah.
So for the first one, would it be fine if we wanted to put 104.7 from the x-axis, or would you prefer 14.7 from the
Oh, no, I always prefer ones that are less than 90 degrees. I think they're easier to work with in terms of the physics. If you put, what'd you say, 104.7. I get where you're going with this. And that's the, kind of the traditional mathematical way, always measuring your angle from the positive x-axis. But that doesn't serve us very well for a lot of the problems. A lot of the problems are served much better by always having an angle somewhere between 0 and 90 degrees and then just label it. It's okay, it's over here in the second quadrant and it's from. Yeah, a lot easier to picture, a lot easier to understand the next step that's going to happen in the problem. And I think it's a lot easier to connect to the physical world and keep doing what I call reading the mathematics. All right, does that make sense here? Let's look at a couple more pictures here. If I've done this right, then, and maybe I'll continue to add with that picture here. I have done both an addition and a subtraction. Let's see what I have here so far. So, redrawing that coordinate system here. Okay, so this being R1 and this being R2. Okay, so here's R1. Here is R2. And I think you caught that this right here, about 20 minutes ago or so, we called this the resultant vector. We called this the two added together, right? Let me put it right here. Resultant vector is R1 plus R2. What do you think I'd get if I took R2 plus R1? Same thing? Agreed, right? I mean, it's still not here on the board, but we kind of got the opposite right here. But we would have still put x's with x's and y's with y's. Just the order would have been reversed. But you already know that if I took 3 plus 5 and I just switched the order, 5 plus 3, don't I get the same thing? If I were to draw this picture, if I were to draw R2 first, wouldn't that be R2? And then R1? So, of course, graphically, maybe I should say pictorially, wouldn't it come out to be exactly the same thing? Maybe some of you recognize this as a parallelogram. We call this the parallelogram method. It doesn't matter which one you draw first. You can draw R1 and R2 and then the resultant, and then you just have a triangle. But sometimes it's kind of nice to draw the R2 first and then the R1. And so you get a parallelogram. And then notice the diagonal of the parallelogram is the sum of the two. Okay. That's going to help us at times. That's a kind of a pictorial representation. Draw the parallelogram. Draw R1 and R2 and then switch the order. Draw R2 and then R1. And then draw the diagonal. The diagonal is the sum of the two. But let me not stop there. What about vector A? Isn't vector A then the subtraction of the two? Now, of course, on that earlier picture, I drew R2 that way, and then this was A. Fair enough? But wouldn't R2 be from here to there? Watch this for a moment. What if I drew an arrowhead from from here to there, the other diagonal of the parallelogram? Let me call it question mark for just a second. What is question mark? Well, wouldn't it be R1 plus what? Negative R2? This would be R1, but here I'm going against R2, right? So I would be adding the opposite. Isn't that the subtraction then? And what I'm trying to show you here is pictorially, it's nice to draw the parallelogram. Here's why. If you draw along one diagonal, that represents the sum of the two. Guess what the other diagonal represents? The difference between the two. And so that vector is really a vector. And my picture doesn't show it, but if I had drawn it right there, it would look like that, right? And so this vector here, A, of course, drawn off to the side, is kind of nice, sometimes, to draw with inside of the parallelogram. And so when it's inside my parallelogram, I have that. All right, well, in the balance of time that we have, and maybe even leading a little bit into Wednesday, let me turn to the back of the book here. Let's see if we can put a couple of these together and see if our newfound mathematics, I-hats and J-hats, make any sense to us. Like I said, the point is to get you really ready for that question about what if we change direction. And I guess I didn't finish. That's the last step. I almost forgot the most important part. So, can we finish this question we started an hour and a half ago? The car is going 20 meters per second to the north. A second later, it is going 20 meters per second to the east. Could you tell me the acceleration? And the whole point of this chapter and this hour and a half discussion is we have just learned how to deal mathematically with direction. When we started the class, the first thing I gave you was two speeds in the same direction and said, could you tell me the acceleration? And you did. You subtracted them, right? And let's do the same thing. I'll give you those two speeds and you subtract them. Of course, this time you're subtracting them with direction. And so maybe I'll go back to an hour and a half ago, right? Remember I said, okay, here is the car initially going 15 meters per second. A second later, it was 17 meters per second. I asked you for the acceleration, and we did 17 minus 15 in 1 second, and we came up with 2 meters per second each second. Perhaps if we added a little bit to this with our direction, although I don't think it's really necessary for this problem, it would look something more like this. It would be 17 meters per second in the I-hat direction, minus 15 meters per second in the I-hat direction, each taking 1 second. And so 17 in the I-hat minus 15 in the I-hat. Yeah, they have I-hats, but they're still like terms. So you end up with 2 meters per second I-hat, which comes out to 2 meters per second each second in the I-hat direction. So you're saying that the acceleration is still 2. And you're saying it's in the I-hat direction. So I would say that here and here you're really saying the same thing. You're just putting a unit vector there to say, okay, that is the x direction. So be it. I'm not even sure the I-hat's needed because, look, we're just talking about a one-dimensional problem. But the problem I'm asking you to do, if I take a compass rose here and call this, what is it, never eat soggy waffles, and say, all right, I'm going to start off with this car going in this direction, and that is my 20 meters per second, and I'm going to give it a j-hat. Let me call that the initial velocity. And then we make this turn. And so this is my second vector, 20 meters per second in the I-hat direction. I'll call that my final velocity vector. And like I said, this whole discussion, this whole hour-and-a-half discussion is, could you now subtract those two? This was easy. This one some of you balked at and said, ooh, what is 20 minus 20? Well, that's just the point. It is not 20 minus 20. It's not even 20 meters per second minus 20 meters per second. It is 20 meters per second in the I-hat direction minus 20 meters per second in the j-hat direction. And so the acceleration would be, and direction is going to matter, so I will put a vector on top. But it would be then the final vector minus the initial over the time taken. And that was, like I said, the whole point we got started here. Is could you do a subtraction where the issue is directional change? And so this final speed is 20 meters per second in the I-hat direction, and the initial is 20 meters per second in the j-hat direction, all taking 1 second. And in this case, this is one of the easiest calculations we can now do because they're not even like terms. One's an I-hat, one's a j-hat. You can't put anything together. They're straight along the axis, so I don't have any of those components. This is much easier than the examples I was showing you. I mean, this is just simply what? 20 meters per second squared in the I-hat direction and 20 meters per second in the j-hat direction. That's what the math says, right? Now, let's read the math a little bit. What is this really saying? Why don't I start with the minus 20 meters per second in the j-hat direction? Because when this thing started off, the car was going 20 that way. A second later, what am I doing? How much am I going that way? None. So essentially what you have said in terms of the vertical motion here is you were going 20 and now you've come to a stop. You have changed by 20 in 1 second in the y direction. You are no longer going in the y direction. That's exactly what this means to me. Lose 20 meters per second in that 1 second in that direction. I was only going 20. If I lost 20, I've got nothing now. And exactly my point. I'm going no speed in that direction. And look at the other term. What does this one say? And it's got a little plus out in front. So it says increase your speed by 20 meters in 1 second in the x direction. And that's perfect because when I got started, when I was going this way, how much speed did I have that way? 0. So after 1 second, I now have 20 in that way. And so this is saying both things occurred. What it is saying is I have lost 20 in this way. I have gained 20 in that way. That's the acceleration. And if I put a grid up here, 20 in the x direction looks like that. Negative 20 looks like that. So my acceleration looks like that, right? That's my acceleration vector. It's the difference between those two. And in fact, if I do the parallelogram that I was just talking about, I'm now covered with the screen. If I were to make this a parallelogram, which in this case would now be a square. But this diagonal should be the two added together. That's not what I'm interested in. It's the other diagonal. Isn't that diagonal the difference between them? Doesn't that look like that? Sure. And so there is the difference between those two. So mathematically, if I wanted to get the magnitude of that acceleration vector, I would go 20 meters per second each second, and I would square that. I would then go 20 meters per second each second and square that. And then I would take the square root. And grabbing my calculator, I can finally answer this question: what is the numerical value of my acceleration? So 20 squared plus 20 squared, taking the square root of all of that, gives me 28.3. And I'm not so sure that anybody would have just guessed that off the top of your hat. I go 20 meters per second this way. A second later, I'm now going 20 this way. What's my acceleration? 28. Sure, 28.3. What else could it possibly be? All right. And it's not so obvious, I don't think, it's 28 until you run through and you see that it's the hypotenuse of an isosceles right triangle. And then you realize it's just 20 times the square root of 2. And oh, that makes sense. Because what essentially I've done here is I have, if I slowed down this way, I have an acceleration that way. And I sped up this way, so I have an acceleration that way. I have a 20 back and a 20 that way. So not only do I know its number is 28.3, but its direction is southeast. Right? And so now, by using these I-hats and the J-hats, I can tell you its value and its direction. And so for some of you, you've now just learned, or you will be learning as you do the homework, a skill that is a very important skill. Not only can we apply the mathematics to our numbers and our units, but also direction. And we can start to answer these things. What is the change in velocity when you go from north to east? Even though the speed remains the same, the direction did change. And because the direction changed, there is an acceleration. And now we can handle changes in direction as well as changes in numbers. Well, that's what I wanted you to see here. I think it's probably worth maybe looking at least one of these here. Why don't we look then into chapter 3 and go to, I got number 4 here first on my list. But let's put this into practice here. And start putting these I-hats and the J-hats together. And even three-dimensional ones too. But that's not going to be our focus. Our focus is more two-dimensional. But like I said, there are 2 homework assignments you have that make you look at three-dimensional. And of course, once we get the hang of this mathematics, now we're really ready to go into chapter 4, which is, can you apply these two-dimensional equations to a ball going across the room, or a satellite that is orbiting the Earth? That's this idea here. All right, so let me start off with number 4. It's not a overwhelmingly powerful one, but it'll give us a chance to get started. Then on Wednesday, we'll finish with a few more examples here from Chapter 3, but then finally we'll get where I really want to begin is with Chapter 4. And by the way, your test is coming up after Chapter 4. Not immediately. Remember, we got that holiday, so there's a little bit of lag time here between we finish 4 and when you have the test. And maybe that's good. Get a little time to sink in. Although, same time, we'll be moving on to Chapter 5. But look at this one here. Here they give you, they kind of mix the Cartesian coordinates or rectangular coordinates with the polar coordinates to kind of make you think this one through here. But it says the rectangular coordinate system is given by the point 2y. So they give you the x value but not the y value. All right, so if I took a grid here and put x and y for the Cartesian coordinates, they're saying here is the number 2. Okay, so there's the x-axis. And they don't tell me the y value. So what I know is this point is somewhere along that dotted line there. It's 2 over, but who knows if it goes up or down. I don't know the numerical value of y. But the other thing they say is that this same point listed in polar coordinates is some distance away, unknown, r, but at an angle of 30 degrees. And they say positive 30, and I think they're referring to the traditional x-axis, so that would be something along this dotted line. And so that would be r and 30 degrees. So obviously, if it is going to be on both of those lines, it must be where those two lines cross. So there is the point P. And we do not know this distance r, but we know this angle is 30. We know this distance is 2, but we don't know that height y. And so they've kind of given us information partly in Cartesian and partly in polar. I must say that's not the normal thing we'll come across when we do a problem. When we do a problem, it starts off where we know both its magnitude and direction and polar, and we got to go to Cartesian. Then we finish the problem knowing both Cartesian, and we got to go to both polar. But just to see if you can put this all together, here's what they're going to say here is, can you find your y and your r? And so in this case, sure, I would probably start by looking at a triangle and realize that I know one side of this triangle. So I would pick a trig function that would use this one and find the other one, which cosine would give me r and tangent would give me y. And so, well, maybe I'll do tangent. So tangent of 30 degrees should be y over the x of 2. And so grabbing my calculator here, I've got tangent of 30 degrees and then multiplying it by 2, I get a y value of 1.15. Cosine of 30 would give me the adjacent, which is 2, over the hypotenuse, which is r. So r would be 2 over cosine of 30 degrees. And of course, actually, once I solve for y, there's got to be a dozen ways of how I can get there, including Pythagorean's theorem there. So I've got a lot of options once I've done that. So 2 divided by cosine of 30 degrees comes out to be 2.31. So there's your conversion. And so that's kind of first on my list. And maybe that's a good place to stop here for today. And I'll just call it quits. And I've got, looks like, a couple more here. 1, 2, 3, 4 more. We'll do that when we come back on Wednesday.